Today we discuss about Banach space. We show that Bxy is Banach space. So we first start from one theorem. We write the statement of this theorem. Theorem is let X be a normed space and Y be a Banach space. Then Bxy is a Banach space. We have to prove that, or we have to show that. So how we show Bxy is a Banach space? First we do in this way. Let Tn be a sequence, be a sequence, be a Cauchy sequence, be a sequence which is Cauchy in Bxy, in Bxy. Okay. Then 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 norm of Tm minus Tn equal to tends to 0 as Mn tends to infinity. So for x belongs to x, we get norm of Tnx minus Tmx equal to norm of Tn minus Tmx less than equal to norm of Tn minus Tm norm of x tends to 0 as Mn tends to infinity. So norm of Tnx is a Cauchy sequence. Now we're going to further discussion. Since y is complete, then Tnx is convergent in y, for each x belongs to x, Now define Tx to y by Tx equal to limit n tending to infinity Tnx belongs to y for all x belongs to x. Okay, we have to show that T belongs to Bxy. We have to show that T belongs to Bxy. Okay, then Bxy is a Banach space. That means Tn converges to T and this T belongs to Bxy. Then Bxy be a Banach space. How we see T belongs to Bxy? First, we show that linearity of T. Let xy belongs to x and alpha belongs to k. Then T of x plus y equal to limit n tending to infinity Tn x plus y equal to limit n tending to infinity Tn x plus Tn y equal to limit n tending to infinity Tn x and limit n tending to infinity Tn y equal to Tx dy equal to Tx plus dy. Okay, now we erase the above portion. Now we say that T of alpha x equal to limit n tending to infinity Tn alpha x equal to limit n tending to infinity alpha of Tn x equal to alpha limit n tending to infinity Tn x equal to alpha Tx. Okay, now we discuss about boundedness of T. Then this one hold means T is linear. So T is linear. Now we is lower portion and we also do boundedness of T. We show that boundedness of T. Okay, how we show that? Note that Tn be Cauchy in Vxy. Okay, first let this one. Hence Tn is bounded because Cauchy sequence is bounded. Hence Tn is bounded. Okay. Then there exists k. Then there exists k belongs to 0 infinity such that norm of Tn less than equal to k for all n belongs to n. Hence norm of Tn x less than equal to norm of Tn norm of x. Okay, for all x belongs to x and n belongs to n less than equal to k norm of x for all x belongs to x and n belongs to n. Now taking limit as n tending to infinity. Now taking limit as n tending to infinity, we get norm of Tx less than equal to k norm of x. Okay, for all x belongs to x. Then we show that norm of T is bounded. Norm of T is bounded. Okay, since norm of T less than equal to k. Okay, we write here then better, but we write direct. So this implies that T belongs to Px. Understand? Next, we erase this problem, our portion, because we saw that t belongs to bxy. Now we do further. So we erase this portion. Now what we do? Let epsilon greater than 0 be given, and since Tn is Cauchy, then there exists n0 belongs to n such that norm of Tm minus Tn less than epsilon for all mn greater than equal to n0. Okay, and this implies that hence norm of Tnx minus Tmx less than equal to norm of or equal to norm of Tn minus Tmx. Okay, less than equal to norm of Tn minus Tm norm of x less than epsilon norm of x. Okay, for all in this one, for all mn greater than equal to n0, for all mn greater than equal to n0, for all mn greater than equal to n0. Okay, and x belongs to x also. Now taking limit as m tending to infinity, taking limit as m tending to infinity, we get norm of Tnx minus norm of Tx less than equal to epsilon norm of x. Okay, then what we do here, n greater than equal to n0 and for all x belongs to x. Okay, this implies that norm of Tnx minus Tx by norm of x less than equal to epsilon for all n greater than equal to n0 and for all x belongs to x where x not equal to 0. Okay, now we do this taking supremum. Okay, supremum of x belongs to x not equal to 0, norm of Tnx minus Tx by norm of x less than equal to epsilon for all n greater than equal to n0. Hence what we get? We erase our portion here. Now we get norm of Tn minus T less than epsilon less than equal to epsilon for all n greater than equal to n0. This implies that Tn minus T tends to 0 as n tends to infinity. So what we get? We get Bxy be complete. That means we take a Cauchy sequence Tn and we show that Tn converges to T where T belongs to Bxy and Tn belongs to Bxy. So we do this problem. Bxy is Cauchy complete because every Cauchy sequence is convergent in Bxy. So Bxy is complete. Hence Bxy be a Banach space. Okay, so we do it so easily. This one is an important theorem in functional analysis. When bxy is Banach space, when x is normed space and y be a Banach space, then we show that bxy is Banach space. Why Banach space is needed? Where y, since y is complete, then t and x is convergent. That means Cauchy sequence convergent just for t and x a Cauchy sequence, and which is convergent. How which is convergent? Because y is Banach space, so every Cauchy sequence is convergent. Okay, so we do this proof. Now we're going to further problem. We show that we know about that any that means any bounded operator from one space to space are denoted by bxy. But if we write here any operator x to k, that means bxk, where k be the field. Okay, where k will the field and also k Banach space, then it is the dual space of x. Okay, and it is called denoted by x star. That means this one is denoted by x star, dual space of x, dual space of x. Okay, from any map of x to k. Okay, any map x to k, this belongs to this one, then this x star bxk contains some g is called the dual space of x. Okay, now we're going to further discussion about some proposition. We erase this problem. Now we're going to further discussion of a proposition. We write the statement of this proposition first. Okay, now proposition, let xy be normed spaces, let xy be normed spaces, normed spaces, and t dt subset of x to y be a bounded linear operator then we have to show that first nt where x belongs to dt, tx equal to 0 is a subspace of x, is a subspace of x. And number 2 we show that nt be closed. Okay, so we know about that. First problem we also discussed in previous class. If this one is a subspace of x. Okay, how we discuss this one? This one is so easily we tell about in previous class. Nt is a subspace of x. We construct in this way: x1 x2 belongs to dt, then tx1 equal to 0, tx2 equal to 0, and so we construct here alpha x1 plus beta x2 belongs to dt because dt is a subspace. Okay, then we write t of alpha x1 plus beta x2 equal to t of alpha x1 plus t of beta x2 equal to alpha of tx1 plus beta of tx2 equal to alpha 0 beta 0 equal to 0. Hence alpha x1 plus beta x2 belongs to the nt. Okay, here not dt, here nt. So nt be a subspace of x. Now we're going to further discussion. Okay, now we're going to further discussion. Second portion, ntv closed. How ntv closed? We know about that. We know that if x dx 2y dy is continuous if and only if is continuous if and only if inverse a is closed when a is closed in y. If inverse a is closed in x when a is closed in y. Note that t is continuous. Note that t is continuous. Okay, and this singleton 0 is closed in y. Then t inverse 0, then t inverse singleton 0 equal to nt. Okay, t inverse singleton 0 equal to nt be closed in x. Too easily we discuss this one. Now we're going to one exercise or one example where nt is not closed. Okay, why nt is not closed? Because if this necessary condition t is bounded is not hold. Okay, we're going to this example now. This example shows that if t is not bounded, so t is not closed. T linear but not bounded, so t is not closed. How we discuss this one? We write first this example. Let x equal to c double 0 be the normed space with norm infinity. Be the normed space with norm infinity. Okay, and define tx to y and define tx to r by tx equal to t of x1 x2 dot 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 xn 0 0 equal to summation of xn n equal to 1 to infinity. X belongs to c double 0. Then we have to show that then first t linear, second t unbounded, third t not closed. Okay, sorry here nt not closed. Okay, then how we do it? Simply we show about that. First we know about that in previous class we also discussed this one. T is linear and T is unbounded. Okay, we also saw in previous class, also known about that T is linear and T is unbounded. Now we're focusing on just last part, NT is closed. Okay, so we just focusing on last part, NT is closed, because these two, T is linear and T is unbounded, we also saw in previous class. So if any doubt, we also see previous class, then also understand these two problem, T is linear and T is unbounded, how we obtain. But now we discuss about NT is closed. Now NT equal to x belongs to C double zero such that Tx equal to 0. This implies Tx equal to 0 means this implies x belongs to C double zero such that summation of n equal to 1 to infinity xn equal to 0. Okay, now what we do, let we construct xn be a sequence in NT defined by x1 equal to minus 1 1 0 0 dot dot dot, x2 equal to minus 1 half half 0 0 dot dot. In this way we write xn equal to minus 1 1 by n dot 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 1 by n 0 0 dot. Then this sequence, this xn converts to x where x equal to minus 1 0 0 dot dot dot, and these are all belonging to, these are all xn and x both belonging to C double zero. Okay, but x does not belongs to n. Her xns are belongs to nt, but x does not belongs to nt. Okay, then what we tell about that, then we tell about that nt is not closed, because one sequence converging to x and both are belongs to C double zero, but xn belongs to nt but x does not belongs to nt. This implies that nt is not closed. Okay, so today we discuss so important topics. These topics are too not too easy. NT is closed, and one example, NT is not closed if T is not bounded, and also we discuss as BXY be a Banach space. Okay, now we also going to further, but today we also not discuss more. Today here is we stop here, because we discuss more topics now.